Okay, can you hear me?
Very well.
Oh, great. Whatever it is, good day, good morning to everybody. So I'm going to spend about 25 minutes or so talking about these breakthroughs in artificial intelligence that are being accelerated by computer architecture. So why is artificial intelligence beginning to work so well? Because it's been around since the 1950s. Well, really, artificial intelligence, the classic version of it is kind of a top-down idea where you, the original idea is you'd write all these rules down, and if you got the rules right, then intelligence would emerge. But within that large AI community, there's a group of people who thought, well, that can't work. You can't get the rules right. We have to learn the rules from the data, so going bottom up. And so it's gone back and forth whether top-down or bottom-up is going to win in the community, but more recently it's been bottom-up. And then actually within the machine learning, there's a subset of it that's doing things based on supervised learning, where the data is labeled with the results and you model it with what's called a deep neural network to be able to figure out those rules from bottom-up. And this neural networking approach has two pieces. There's training, where you give it the labeled data and it learns the rules from it. And then after you develop the rules, you apply it, and that's called inference. And it's the green subset, the deep neural network, is what led to Hinton, Bungio, and LeCun to win the Turing Award the year after Hennessy and I won it. So that's tremendous excitement after years at work on it. So how do we keep it working well? Well, the first word in machine learning is machines. So we need more data and faster machines. It's data driven, so we need lots of data. No problem getting data in the modern world. Between cloud computing and Internet of Things devices, there's a huge number of data sources. What about faster machines? Well, Moore's law is slowing down. And so this graph below shows general purpose microprocessors is how many transistors there. Moore predicted doubling number of transistors every 2 years in 1975, and this is how far Intel's off. If they were on top of it, we would have 15 times as many transistors as today. So the number of transistors turns into performance, the way most people think about it. So in the 1980s and 90s, performance was doubling every 18 months. So back then, if you had a desk-side computer, after a year, your friend's computer would be so much faster and they get their work done so much more quickly that you'd throw your perfectly good computer away because the new one was so much better. But now it's slowed down with the slowing of Moore's law, so doubling kind of every 20 years. And nobody throws their laptop away today, right? I throw mine away, or I just recycle it when the battery dies, or the display dies, or the disk fills up. But the processor is plenty fast up, and new processors aren't that much faster. Okay, so how are we going to get faster machines if Moore's law isn't helping us? The only way computer designers know to go forward is what's called domain-specific architectures. That is, they don't try to run all C programs in the world, they try to do a few things well. So what's a big challenge is this 50 years of learning how to build general-purpose CPUs, those lessons and experience may not be helpful. So it's an exciting new frontier for computer architecture. So if you're a researcher, this is great. Nobody knows the right thing to do. All kinds of ideas could be good. What an exciting time. However, if you're a company and selling products and trying to make money, this is pretty uncertain times, kind of scary. Well, which way should we go? Will they buy it? And this is, we need these not only in the cloud where training is done. The training is done in the cloud, but also on the edge where the inference is being done, because both of them need faster machines. Both of them care about the performance per watt in the cloud because of the cost of cooling, and in the edge because of battery life. So what is the cloud and edge? Just in case you guys probably know this, but just a reminder, the cloud is simply remote computing and storage in distributed data centers connected via the internet. So warehouses of 50,000 servers scattered all over the world. And the edge is Internet of Things, things in your cell phones, in your cars, everywhere. Okay. And I'll talk about things for both. Oh, there we go. Okay. So how did Google get started in this? In 2013, Google was a very early believer in the deep neural networking subset of machine learning and artificial intelligence. So they were early adopters. And they saw that if these applications, if 100 million of those customers started speaking to their phones, the edge devices, like to do translation or something, just 3 minutes a day, Google would have to, using just standard general purpose microprocessors, Google would have to double the number of data centers it has. So these buildings, 150,000 computers over, they have to build twice as many buildings and fill up the computers. So not only would that take forever, Google didn't have enough money to do that. So the goal was explicitly in 2014, engineers were designed to reduce the total cost of ownership of neural networking, the inference phase, the serving of it, by factors of 10 over CPUs and GPUs. And so they had this really short development cycle. It started in early 2014, and 15 months later, the engineers delivered this design in the data center and was helping people using machine learning. So that was everything: the architecture, all the software, building it, deploying it. Were they successful? Yes, they were. In fact, they exceeded the target. So the red bar shows the performance per watt over the contemporary Intel CPU of the time. So it had 80 times the performance per watt of the Intel CPU, and it had 30 times the performance per watt of the NVIDIA GPU of the time. So factors of 30 and 80 are amazing. So when we're talking about commercial products, these were not just research ideas. So if you have factors of 2 are a pretty big deal in commercial products. So getting factors of 10 is a very rare for real products, and the TPU-V1 was able to do that. So why was it successful? Well, they had, instead of just a single ALU in typical general purpose microprocessors, or maybe a few of them, it had a 2-dimensional arithmetic unit, 65,000 arithmetic, 2 to the 16th arithmetic units have been organized in a 256 by 256 2-dimensional array. And this could do the multiplies much faster that are, the foundation of neural networks. So the 65,000 arithmetic units. It did things in 8-bit integer instead of 32-bit floating point, which is the norm for on GPUs and CPUs. So it was more efficient not only to compute, it's much easier to compute 8-bit integer multiplies than 30-bit floating point, but also it took 1/4 of the space in memory, which was very valuable. And then, because it was domain specific, it dropped the classic general purpose features that we see in all kinds of CPUs and GPUs, like caches and branch predictors and so on. So it didn't have to include them, saving area and energy, but it also tossed those transistors back so you could have bigger memories and more arithmetic units. And that's the argument for this kind of specialization. So that was TPU-V1, and it was doing the inference. Now, so Google was ready next to take on training, and it's much harder. The computation is more difficult, kind of 3 times as difficult, 3 times as much computation per step. It needs a lot more memory, and the data that you're computing on is bigger. So the question became, what are the good ideas in TPU-V1 that we should reuse in TPU-V2? Well, the first thing is the training takes forever. If we used a single chip for Google's production applications, it would take more than a year to train on a single chip. So since it takes more than a year to train in one chip, obviously the right thing to do was to build a system with a lot of chips. So the Google decision was, we're going to build a supercomputer. So TPU-V1 you'd use one of them at a time, or maybe you'd cluster. They went into CPU hosts as accelerators, kind of coprocessors. And so you could cluster a bunch of hosts together if you had a big inference workload. But TPU1 was designed from the beginning, or TPU-V2 was designed right from the beginning. We're going to build a supercomputer, because the conventional wisdom then and now is the bigger the machine, the more data, the bigger the breakthroughs you can get in machine learning. And the paper that I'm talking about is in the July issue of Communications of the ACM, just this last month issue. So that was a really good idea. The decision was made in, I think, 2016. And so this is a plot from our colleagues at OpenAI about the very, the bleeding edge of training. If you're setting records in training, making groundbreaking new results, the amount of since 2012, it's gone up 10x a year. So remember, Moore's law at its peak was 1.5 per year. This is 10x per year is the appetite for that training. So if you're a computer designer, you love machine learning people, you hate people who say, oh, computers are fast enough, I don't need a faster computer. These people want all you can give them. So what's the main feature of a supercomputer? It's the way you connect the chips together. So the TPU-V2 has 4 custom links built into the chip, and we call them ICI for inter-core interconnect. They run at, each link runs at 500 gigabits per second in both directions, and it's the switch itself and the NIC controllers aren't external to the chip; they're built into the chip. But it only uses about 1/8 of the die, 12% of the die. And this supercomputer was designed to scale up kind of the 256 chips, kind of like Lego blocks. Just plug it together, 256 chips. They have to be adjacent for it to work. And here's a picture of 256 of them. And the picture at the bottom is the board. And I don't know if you can tell from the picture, but those are heat sinks that are very tall because it dissipates 280 watts. So the other way we could have done it is use kind of Ethernet and standard data center networks. But if you compare to these ICA links are much faster, at least 5 times faster. You don't need a separate interface chip, or you don't need separate network switch hardware. So that makes it cheaper and also reduces the latency. There's fewer bottlenecks. And so it's maybe 5 times the bandwidth at 1/10 the cost by building the interconnect into the chip itself. So how many cores you have on? That's how you connect the chips together. How many cores are in there? Modern server cores could have 30 or 40 cores, and GPUs have 80 cores. So how many should be done? So we went back to the advice from Seymour Cray, the greatest supercomputer designer of all times, and when people were asking him how many cores does he have in his supercomputer, and he said, if you were plowing a field, what would you rather have? 2 strong oxen or 1,024 chickens? Basically making fun of people who had wimpy cores. So because as you improve the technology, the wires don't scale as well as the transistors for logic and memory. So relatively the delay increases. We already know training can use lots of processors. The decision was to use 2 cores per chip to keep them smaller so they could be faster. Thinking it'd be a lot easier to write the software if each chip, if we're going to have 256 chips, it'd be easy to write the software if there's 2 cores per chip rather than 1,000 wimpy cores per chip. So that's the interconnecting cores. How about computer arithmetic? Well, one of my colleagues at Berkeley, Velvel Khan, won the Turing Award for his contributions to the IEEE floating point standard. So I never expected to be involved in any project where we would change the floating point arithmetic. That's kind of sacrosanct. Remember, the success of the TPU-V1 was this big 2-dimensional array. But it did it with 8-bit integers. We couldn't have done it with 32-bit floating point. So it made sense to go try 16-bit floating point. But the 16-bit floating point and the 16-bit floating point, if you do a design, typically would be like 8 times faster than 32-bit floating point using the same number of transistors. So you get a big advantage there, and you bring the size down so you could put it into array. But they wanted to see if the standard IEEE floating point, which is shown below in the slide, would work for machine learning training. And it turned out it didn't work very well. By the problem was that exponent is only 5 bits, right? So you can only represent 2 to the 32. I mean, you can only represent 32 different exponents, so you can't get them that small. So what would happen when they used it is they'd have underflow, as you can't represent small enough numbers. So what they decided instead is to go with an 8-bit exponent, which is the same exponent size as the single position floating point, so that they didn't have that underflow happen. They could represent very small numbers, but they didn't need that much precision. Instead of the 23-bit precision of IEEE floating point, they could get away with 7 bits. So they could pack it into 16 bits, and the key thing have the really big exponent, and they call that format brain float. And when you think about it, the multiplier doesn't multiply the whole 32-bit number, it just multiplies the mantissa. So by being 7 bits instead of 10 bits, and you square both of those, it was half of the die size and half of the energy for floating point, and it worked better for software, which is a pretty rare combination. So easier for hardware and easier for software by inventing a different floating point arrangement for machine learning to use in the supercomputer. So what chip designers call the floor plan is shown on this slide. The little purple rectangles are in the corners are the ICI link interconnects. There's 4 of them per chip, so in the corners. There's a little bit of logic to control it in there. And then the matrix multiply units are only 10%, and there's 2 of these per chip. There's 2 of these per chip. The tensor core, we call them as the upper and the lower one. There's the 2 per chip on that die. Now, that was done pretty quickly, and the designers decided they weren't thoroughly happy with how it's done, so they thought, let's do a second one really quickly. So usually there's this kind of joke in computer science called the second system effect, where it worked for the first one, and so then you're self-confident and you just put everything in the second one and it doesn't work. Well, they did the opposite of that. They wanted to do it quickly, get it out in a year, and made very minimal changes. They were able to get a faster clock rate, make the ICI interconnect bandwidth faster, and a faster memory system. They're all about a third faster. They thought they could double the number of matrix multiply units per core, and they would do that as well. So if it's 1.35 times faster and twice as many multiply units, the peak performance went up a factor of 2.7. To get the faster clock rate, it used more power. In fact, it used so much power they couldn't air cool it, so they liquid cool it. So in the middle of the slide is a picture, and those are what looks like really thick wires are actually pipes that move the liquid to cool the chips, so they don't have heat sinks anymore. They have double the memory bandwidth, and they made the supercomputer you can build 4 times bigger, so they can connect 1,024 chips. But because they were redoing the second design from the floor plan, the die size grew less than 10%, and it was in this very same technology. All right, how fast does it work? Well, the first thing before you talk about the supercomputer is you'd like to tell how fast the chip works. And in computer architecture, we don't know how to judge it on an absolute scale. It's kind of grading, using professor talk, you grade on a curve rather than grade on an absolute scale. So the question is, how well is it to the contemporary GPU of the time? And the contemporary GPU is the NVIDIA Volta. So the benchmarks are 2 halves. The upper half is a standard benchmark that Google helped get started called MLPerf. So this is an industry-wide standard. So Google submitted its results and NVIDIA submitted their results. And if you can see, the geometric mean is the same. So basically, at a chip level, the TPU v3 and the Volta are the same speed using the MLPerf benchmarks. But the lower half of the slide has Google's production applications, and that's what we care about, is production applications. Well, these are running like 5 times slower, or the TPU v3 is 5 times faster. How could that be? How could, when NVIDIA does it, we're the same speed and not? Well, it goes back to that computer arithmetic. So I remember I told you it's easier for software to use BrainFloat. So Google apps just use BrainFloat easily. It takes extra work to do the standard IEEE float, which is in GPUs. They don't have BrainFloat in the Volta GPU. So it's extra work because you get these gradual underflows and you have to do what's called loss scaling. So none of the people in the production applications wanted to do that at Google. And so we wondered just how popular is these IEEE floating point that goes really, for the 16-bit version, that goes really fast on the Volta GPU. How many people use it? So we don't use it, and we talked to people at the Vector Institute in Toronto, Canada. This is 200 leading AI researchers who have lots of GPUs. And only one of the 200 researchers ever used the 16-bit floating point format because it was extra work to make it work. They just used the 32-bit, so it runs much slower. So the Vector Institute's experience with Voltas is like ours. So keep that in mind. So that's the single chip performance. Oops. All right. There we go. Oh, too far. Okay. But if a classic way to measure supercomputers is to say how much speed up do you get when you run the applications on the computer. So as you scale up from one chip to 256 chips to 1024 chips, what fraction of that performance do you actually get? Do you get 250 times the performance for 250 chips, or how's that work? Well, remarkably, on 4 of the production applications, you get almost perfect schema. A 980x speed up with 1024 chips, or 1015 speed up. So 99% or 96% of perfect speed up. So it's just remarkable. It's results you don't usually see. And I think this has to do with the ICI links help a lot, and actually just mapping machine learning to the application. Okay, there we go. Now, when we, how about comparing it, this training supercomputer for deep neural networks to a conventional supercomputer? And it's not a perfect explanation, a perfect thing, because supercomputers run LINPACK, which uses double precision floating point, 64-bit floating point. And also, LINPACK is kind of a bad benchmark. They have synthetic data and lets you scale up the data. It's called weak scaling. They have as much data as you need to keep your computer busy. So they're solving 1,000, a 10 million by 10 million dense matrix. I don't know how many people have that problem. On the other hand, Google is running AlphaZero. This is the program that beat all humans in the world at both chess and at Go, and is the champion program. And it's using real data, but it's not double precision data. It's BrainFloat 16 and 32-bit data. So keep that in mind. It's not apples to apples. Nevertheless, this supercomputer for machine learning, it's domain specific, remember, is able to get 70% of the potential. So if you take 1024 chips and you say that, what's the peak performance? It's delivering 70% of that, 1024 times 100% peak performance, which is remarkable. You can see traditional supercomputers there in red and yellow usually hit about 60%, which is good. And they do that because LINPACK can scale it up. How many petaflops per machine? It's almost 90 petaflops for TPU v1 versus 60 for this traditional supercomputer. It's the number 4 supercomputer in the world, and it's if we could submit a machine learning supercomputer to it, but in terms of flop rate, it would take over. But the other interesting measure for the top 500 is what they call the green 500, where you factor in the performance per watt, and there it really shines. So we're 50 times the performance per watt of the number 4 supercomputer, and the most efficient traditional supercomputer, the number 1 in the green 500 list, is 15 watts. We're 10 times better than that in terms of performance per watt. So very impressive there. Okay, so that's the cloud. What's happening at the edge? Well, at the edge, the same things are happening. They are extending standard microprocessors with enhancements for artificial intelligence. So here are 2 examples. The one on the left is from Alibaba. The thing that they call Black Iron, or Zhanti 910, is using something called the RISC-V architecture. And the board on the right is from a little startup company called Ours, and it's also using the RISC-V architecture enhanced for AI. And this board, remarkably, is less than $3 US or less than 20 yuan to do that. So this is at the edge. So what's AI at the edge in RISC-V? What is that? So just reminds you that about your computer architecture textbook. So when software talks to hardware, it has to use a vocabulary, and that vocabulary is called the instruction set, or the instruction set architecture, which computer architects often abbreviate as ISA, or pronounce it as ISA. So up until recently, all instruction sets, all of these vocabularies were proprietary. So to talk to hardware, you had to pay somebody a license fee. It was the two most popular are Intel, which dominates the cloud, and ARM, which dominates the edge. So we've had popular open source software for at least 20 years, with Linux as a prime example. Well, why not could we do something if we had an open ISA, an open instruction set? Well, that would allow open implementations of processors, and we could have open source hardware as well. And so that is what RISC-V is enabling. And so there's two, so let's talk about what are the interesting features about RISC-V. Well, first of all, it's called RISC-V because there are 5 projects at Berkeley on RISC-V. There are 4 of them in the 1980s, and then starting in 2010, my colleagues, Krista Osanovich, and 2 STAR graduate students, Andrew Waterman and Yunsep Lee, decided they were going to build another RISC project, and they named it RISC-V in honor of the 4 prior projects, and I helped mentor them to do that. So here are the features, the 7 features of RISC-V that are really different and I think important. Number 1, it's free and open. Anyone can use it, which is going to lead to more competition and I think more innovation. What it means for startup companies is, with proprietary instruction sets, the first thing you have to do is negotiate and sign a contract. That contract can be very important because if you build a successful product, that could lead to a lot of money, so you want to be careful how much you pay. So those contract negotiations can take 6 months. With RISC-V, you can just start using it, and you can later figure out who you're going to, whether you're going to use an open source implementation of RISC-V or from a vendor, but you don't have to start your contract negotiations. You also save the money, right? That doesn't cost you anything to do that. Both of those things are attractive for startups. It's for both the cloud and the edge, from the largest computers to tiny. It has both 32 and 64-bit address versions of it, which, it's not surprising, it's just important. Even though it started in 2010, we knew that we wanted to be able to enhance the instruction set with domain-specific applications. It was hard. The microprocessors were slowing down. We knew that was the future. So we purposely left room for it to able to evolve. If you plan for that from the start, it's easy to do, but otherwise it's very difficult. It's like trying to pack clothes into a packed bag. If your opcodes are all filled up in the machine instruction set, so there's no place to stick new instructions, then it's hard. But if you plan for it, it's pretty easy. A really different feature is it's modular. Prior to this, all instruction sets are kind of like people. As you get older, you get wider, right? You get bigger and heavier. That's true for instruction sets, is because they want to maintain compatibility. Every time they add a feature, it's with that architecture forever. It's there for the rest of its life. So it gets bigger and bigger over time. So Intel adds, on average, when I last looked at it, it's like 2 instructions a month over its 40-year lifetime. And you have to do it all. With RISC-V, there's optional extensions that you can add or leave out because the software runs on a core set of instructions. It's guaranteed. All software runs the core operating system, compilers, and all that. So you get a giant software stack if you just implement the core. And that core itself is a nice, simple, elegant core. It has about 40 instructions, which is tremendously simpler than ARM and RISC-V, which means it's going to be easier to build fast, efficient, and small chips for Internet of Things. And then the next difference is part of being free and open is a community evolves the instruction set. Just like the Linux has the Linux Foundation, we realized we wanted to have a foundation. It's called RISC RISC-V International, and it owns the instruction set. So after the graduate students left, academic projects can wind down. This is sustaining the instruction set. And then more recent people are attracted to it is that they're worried about what's in their hardware. So some countries are worried about buying hardware from other countries, so they want some of their technology to be homegrown. So by being an open instruction set, they can build it themselves in that country, or if they feel more comfortable, they can get an open design, and from the open design, you can see what's, from looking at the register transfer language, you can see what's in there before you fabricate it. So RISC-V, it has probably 600 members now in almost 50 countries. There's, I think, 6 or 7 companies are the premier ones. There's a lot of them in China, but it's a worldwide phenomenon. You can see there are people all over the world. I just wanted to do a second to explain a common confusion about RISC-V is about the difference between open source hardware and open specifications. So what's on the left-hand side is there's 3 ways to do specifications. So a vocabulary, right, is a specification, right? It's how you speak to the computer. It's not how to design the computer, but the computer has to understand the vocabulary. So you can have it closed like the x86, you can have it licensable like ARM, or you can have it free and open like RISC-V. Well, just those are specifications. How about when you build it? Well, there could be 3 options there: closed, licensable, and free and open. So what's the relationship between the rows and the columns? If you have a closed spec, your only option is closed design. So Intel owns the x86, and it was forced to allow AMD can build microprocessors. But the only thing you can do is buy those microprocessors from Intel or AMD. Okay, you can't have free and open designs or licensable designs. How about the licensable specification? Well, ARM pioneered that business model, and it lets you do 2 things. A licensable design. ARM has designs that they will license to you. They call it IP for intellectual property, but they're core designs in register transfer languages. And talking to people in the industry, maybe they'll charge you $5 million for one of those. If you use the core, you use lots of them on your chip, and a % of the chip. So the royalty play in the chip, like an author would get a royalty. That's a licensable design, getting the designs from ARM. You can also ask for the rights to be able to design your own, which is Apple does. Apple designs their own core, they don't license it. So that might be 25, or I've heard even $50 million for the right to design your own. Okay, but there's no free and open designs because ARM will sue you if you try and do a free and open design because they own it. And then how about this last row? Well, if it's a free and open specification, you get all 3. You could design it yourself and keep it to yourself. That's what NVIDIA is doing. NVIDIA has designed their own core, and they put it in every GPU that NVIDIA does has a RISC-V core inside. There's licensable designs. This is what a startup company that Krista Hasanovich and Andrew Waterman and Yunsuk Lee have done called Sci-Fi. They build designs you can license. Also, Andes does that. And then there's open source design, free and open designs. There's one that comes from Berkeley. There's one that comes from ETH Switzerland. Western Digital, which is putting RISC-V cores in all of the disk drives. They made up their version open. So there's all 3 of them. So this was a long explanation to say, what's the difference between a free and open specification and open source designs? Well, the specification is the instruction set itself. It's like a standard, and then you can use that to build processors, and you could have either closed, licensable, or free and open. Okay, so why do people care about that? Because a lot of the cost is this IP. So this is some data that I showed you that might cost $10 or $20 million to build a commercial ASIC. Today, about a third of that is the intellectual property, and a big piece of that is the processor itself. This is for a relatively simple design. Okay, all right. So what's our vision for RISC-V? Our vision was that in the next 5 to 10 years, it's ubiquitous, that it would be everywhere. You would see it from the tiniest devices up through the cloud, up into the supercomputer. But there's another, kind of sociological goal. Given the opportunity that RISC-V is letting you have open source implementations because the open architecture, right now we're having these kind of Cold War tensions again between countries in the world. And if we can all collaborate in the world around open source hardware, like we do with open source hardware, we can get to know each other and have friends and colleagues and maybe reduce these tensions some. The example I use for US and China is for World War II, 200 American pilots before World War II resigned from the US military and joined the Chinese Air Force to help defend China from the invasion of Japan. And they were referred to as the Flying Tigers. So there's an example of collaboration for better things. So I'm involved in something called the RISC-V International Open Source Library. So you are Portuguese speaking, so I don't know if Rios means rivers in Spanish, where that's where I got the name. Spanish is pretty popular here in California.
It does
so
mean
it's
Portuguese as well, yeah.
It's Rios, okay. So
yeah.
it's the 5-year mission of the Rios Lab is to make the ecosystem RISC-V world class. It's a nonprofit organization, and we're going to measure success by technology transfer. All of our development is open source. We're going to make industrial strength intellectual property, and we're going to try and avoid patent lawsuits while we do this. A lot of people are building processors, but the rest of the chip, some people call the Uncore, doesn't get as much attention. We're going to try and fill that gap. The base funding comes from the city of Shenzhen, and we're getting matching funding and hopefully some loaning of engineers on the open source projects. It's a globally distributed lab, but most of them, the engineers are going to be in Shenzhen at what's called the TVSI, or the Tsinghua University UC Berkeley joint venture that's been located in Shenzhen for several years. The Rios Lab is starting this year. We'll teach about RISC-V, open source courses, and I'm leading it, although I'll be remote. And the co-directors who will be on site is my former student, Zhangji Tan, and Professor Lin Cheng, a former a Berkeley alumnus as well. Zhangji went to Berkeley as well as he went to, and both of them were undergraduates at Tsinghua and graduates of Berkeley, and they're going to be leading it on site at TBSI. So let me wrap it up before we go to questions here. So the big picture here is, with more slowing down, the only way we're going to get faster machines is to do domain-specific architectures, which means tailoring the machine to the domain. Fortunately, there seems to be a lot of things that machine learning can address. So that was just serendipitous that we had to narrow the focus on something that seems pretty general purpose. Google's TPU v1 demonstrated that 50x benefits in performance per watt, which is kind of remarkable. There's lots of people working on AI for the edge with same ideas, of course, with a much smaller budget. We think a lot of those people are going to use RISC-V because you need to expand that instruction set. You want to be able to do that and not be hassled about it. And so that's going to help, encourage open source hardware development. The Rios Lab that I'm involved in is, we think, will be one of the players in that space and trying to help people around the world do that, and like I said, Spanish is Rios for rivers, and we picked that name because it symbolizes, what do rivers do? They collect resources from lots of lands to create this strong force that can change the landscape. Well, we hope that's what the Rios Lab is going to do, is collect resources from all the world and improve the technology landscape. Okay, with that, I'm done. I think I'm ready for questions. So I think I'll stop sharing so I can see people. And I am ready for questions.
All right, David. Thank you. Thank you so much. It was a very interesting presentation. I have a couple of questions coming from the audience already. Maybe we'll start with the first one from Romario. He's quoting Dr. Robert Colwell that says, "The economy will end Moore's law, not physics." And his question is, what do you think about that?
Yeah, that's a great question. The idea is so Moore made this prediction in 1965 and then updated in 75. And what people, but to make it happen, you have to buy new semiconductor equipment. So people, when they saw it was possible, companies like Intel and Samsung would buy new equipment so they could make newer transistors. And so if that, for that to pull off, for that to make sense, because the equipment got much more expensive every time, the volumes had to increase, right? The number of chips you had to sell, but that worked. They'd make the chips bigger, they were more powerful, or they had more transistors, and then people would buy more of them. So that all worked for them. So it was both a prediction and an investment strategy. We got to keep buying new equipment to keep Moore's law sustaining, and more or less they did it for 50 years. Now, if you've been watching the news, Intel has been having a lot of problems. They were trying to go to 10 nanometer technology, as it's called, and really stumbled. Their competitors were able to keep going. So when he says it's going to be an economic thing, the question is, does it make sense to build the next generation of fab equipment to get smaller technology? Will the chips actually be cheaper? How expensive will that equipment be? And what's been happening is the number of companies that can make that inventions has shrunk. It used to be maybe there are 20 world-class fabs or 20 companies building world-class fabs. Maybe now it's 3, right? Intel, TSMC, Samsung. That might be it. And Intel's been having some problems. So is it that they don't have the money? Is it because the ending of Moore's law means the transistors aren't getting cheaper because the improvements in technology aren't as good as the past? But it's the ending of Moore's law or it's slowing down. And there's not like a new Moore's law. It's not like doubling every 3 years. Every technology node is taking longer and lasting longer. So it's kind of like if you were to take your foot off the gas of a car, it would slow to a stop, right? It hasn't stopped. Yeah. But it's getting,
it's getting there,
yeah. It's slowing down for sure.
Definitely. Good question. Thank you. Yeah, it actually was a good one. There's another one coming from Alexandre in Portuguese. He's asking, what scientific papers had the biggest impact in your career in artificial intelligence and why? I would maybe add, if you can comment, taking into account the work that you have done with Google, right?
Yeah, so I'm not an expert in artificial intelligence or machine learning. My expertise is in computer architecture. After I retired from Berkeley, I didn't want to just sit on the couch and watch television. So I started working part-time at Google. I worked 4 days a week there. And fortunately, they put me in this group that was doing machine learning for the machine learning group. And then there was a piece of Google that was building these chips. And so I work at that intersection. So I don't claim expertise in artificial intelligence. So, but I'm a kind of a fan, and I sit near these people who are moving the state of the art. So I learn things from them. Certainly one of the most impressive articles ever was by Gordon Moore. So not only did he in 1965 suggest that it was going to double the number of transistors every year, and a few years later, he wrote an article kind of explaining it. It was more Popular magazine, and he laid out the arguments for what other people have called Moore's law, and he figured out the consequences of it. So in that article in the late 60s, I think, he has a little cartoon. It's showing computers for sale in department stores or grocery stores and computers inside of cars. He kind of figured all the embedded uses of computers, which were inevitable if Moore's law would be correct for the next several decades. So that's a remarkable paper. I remember going to the Berkeley Library and getting a copy of it, photographing it, right? Oh. And then years later, I went and somebody had stolen it because it became valuable. That article was so important that people stole it from the library and, I don't know, sold it online. I think if you had a copy of that magazine that article's in, my guess would be worth $1,000. I don't know what.
I can imagine.
So I think that particular article really stood out. So these are computer architecture examples. Another, and this article was, I don't know, 3 or 4 pages. Another really short, really impactful article was by Gene Amdahl, a computer architect. And in this article, he wrote what's called Amdahl's Law, what other people call Amdahl's Law. And he said, I have a fairly obvious thing to say. If this is your pie chart right here, and this is the piece that's sequential and the rest of this is parallel, you can't go faster. This part's going to limit how fast you go. So if this is 10%, you will not go more than 10 times faster, no matter how many processes you have. And it's a very obvious statement. It's the law of diminishing returns. But computer people today still get, look at the part, and I'm doing this piece 100 times faster. They still run into this kind of terrible Amdahl's Law, forget about the other part, and oh yeah, I forgot, right? So we talk about it all the time. Is there an Amdahl's Law limit here in terms of impact per word? I don't know if there's a more important article that's been written in computer architecture. So those would be two of my favorites.
Yeah, I hope the audience is taking notes. That was a really great answer. So I have here Edson Casemiro asking, well, it's a long question, so let me read it quickly. Thank you very much for your magnificent work. I believe that with all these resources and data, we will soon be able to reach general artificial network, right? But we still have a lot of difficulties to train our algorithms because of the GPU prices. Is it going to change, or the AI field will be just for the giant companies? The Googles, the Microsofts, and the AWSs.
Yeah, I think that's a great question. I mean, right now, what's happening is the breakthrough results in training are gigantic computers. And there's something, I think you may have read about it. Is it GPT-3? This is a gigantic machine with an amazing, I think I talked about the weights that you train. When you do training, your training parameters are weights. Well, this GPT-3 has billion, I think 200 billion parameters, whereas other models might have 100 million. So huge. And it's doing stuff that people are impressed with, right? So we're at the at the early stages where machine learning is starting to work, and we're kind of surprised it's actually starting to be useful, and we're trying to figure out how well it goes. So right now they're using the biggest supercomputer worlds, but this is not sustainable. When I said a factor of 10 increase every year, that's a factor of 100 every 2 years. No company can afford that. You can't increase the resources a factor of 100 every 2 years. So we're going to need to figure out more efficient ways to do the training. And this is the early days. It's kind of brute force is what we're doing right now. So I think there's opportunities to figure out how to do this more efficiently, right? And so this will be algorithms, right? Better algorithms to be able to do this. So if you figure out an algorithm that trains, at the same accuracy, much more efficiently, people will be very excited about that. And I think there's also been some pushback into building these giant training machines and talking about the environmental impact of these computers. So there's real interest in kind of making machine learning kind of green so that it doesn't use as much resources, both so that more people can participate in it, as well as just, to save electricity and the consequences of it. So I'm not an expert in that area, but I know there's a lot of interest in that topic, or at least desire for that to happen. So it's because of the modern world and open access to everything. So you can see the software that Google uses. Google uses TensorFlow primarily, but there's also this software stack called PyTorch, and you can see what's inside these things because it's all open source. So if you have a great idea, there may be some opportunity there that you could innovate and contribute, and people would love it.
Yeah, and David, maybe a follow-up question will be, does quantum computing present itself as a potential solution, and what are the odds looking from a computing perspective, and according to your own experience?
Yeah, so I'm not an expert in quantum computing either, but in fact, it's been around for a while, right? And I was hoping that quantum computing didn't catch on before I retired. I didn't want to have to teach quantum computing. But I think, and when I talk about, the ending of Moore's law, this is a common question: what about quantum computing? Because it's in the newspaper all the time. Right? So that made me go learn about it. I got the questions enough. So first of all, quantum computing is big science, right? This is at micro Kelvin, almost absolute zero. If a truck rolls by, it's not going to work. It decoheres. So it's big science right now. So if it works, it's going to be in the cloud, right? If it works, it'll be in the cloud. We're not going to have a quantum cell phone. So if you cared about Internet of Things devices, we need that. The other question is when. So we know nuclear fusion works. The sun uses nuclear fusion. So people who were in physics got their PhD when I did 40 some years ago, there were people who went into physics saying, I'm going to solve nuclear fusion. That's what I'm going to work on, right? So nuclear fusion is still in the future, right? It still takes more energy in than they get energy out. So they haven't solved it yet. It's great that people want to work on this long time problem. If they solve nuclear fusion, it'll be fantastic for the world, as an energy source. But it's a hard problem. So there have been 2 national reports in the United States, one by the National Academy of Engineering and one by something called the Computer Consortium, that invited experts and talked about what's the state of quantum computing. As I read that, both of them said, well, it's going to be a while before we have an error-correcting quantum computing. So I think it's kind of a 2030 thing. So yeah, I'm glad people are going to work on it. I admire people who work on long-term issues, but it's not, despite what you read in the newspaper every day, it's not right in the corner. And there's some danger, if I think about my career, particularly, there have been fields like artificial intelligence, the top-down version of that made tremendous claims about what was going to happen in the next few years. And then the claims didn't happen. And that led to a pushback and a cut in funding and stuff, because you guys said all this thing's going to happen. It didn't. Why are we funding this? So that they call that the AI winners. So there've been a couple of AI winners where they overclaimed and underdelivered. So I'm a little worried about all the press about quantum computing right now, that if there's not a real useful application for 10 years, whether there's going to be an underinvestment. At the same time, all the big companies are investing in it. Google is, IBM is, Microsoft is, and there's lots of academics. So a lot of people working on it. But, like I said, my guess is we won't see commercial applications until the end of this decade, and we got to do something for now. Of course. Then also, let me just say, quantum machine learning doesn't make sense. It's machine learning, it needs lots of data. One of the biggest problems for quantum computing is the memory system. How do you get data in and out of it, right? There are these micro Kelvin. How are you going to have a storage system for it? So the best problems for it are a lot of computation with almost no data. That's not machine learning. So, okay, that's enough.
That's a different thing. Yeah, of course. There's a question from Richard here. How do you think the usage of RISC-V can help prevent hardware vulnerabilities such as Spectra in future systems?
Great question. So, there's a whole community about security and trustworthiness in our country, and we need it, right? It's embarrassing. We decided, I'm one of the people who decided to try and make computers easy to use and cheap and fast. That was the most important. We didn't really emphasize security. There were ideas that hardware people had 40 years ago about making more secure systems, but people building software, they're building it for PCs, they didn't care that much about it. So the features that were in there kind of atrophied and disappeared. So there hadn't been a big emphasis on hardware security, despite it being a terrible problem. And now we found out these Meltdown and Spectre attacks, that the hardware itself was a weakness. They could figure things out, secrets from the hardware, which was a big surprise. So one of the issues is with proprietary instruction sets, with the 2 biggest ones being ARM and Intel, is you got to work for those companies if you're going to do something in the hardware to make it better. The security community is excited about RISC-V because here's an open architecture that allows open implementations that anybody can try ideas. And in fact, you can download one of these open source cores and the open source software stack and put your modifications in and put it on a field programmable gate array, and those can be pretty economical. And connect it to the internet and try it out. You say, hey, I've got a secure computer. You hackers try and break in, because I think my innovation is going to stop it. And you could do this for, like for $100, you could put a computer up that you claim is secure. So the security community is excited about RISC-V because of the opportunities around it to change it and to investigate it and to try ideas out. And in fact, we have the RISC-V Fund International has a standing committee just on security. And I was just talking to Helena, who runs that organization, that there's going to be a conference this summer, a virtual conference, I guess, where it's going to be about security using RISC-V. And that the whole conference is RISC-V based security. So I think it's a big opportunity going forward to let us have do kind of experimental security around RISC-V. So I think I don't think I can point to something in RISC-V and say, see, that has solved security, but as a vehicle for explanation, it's kind of got extraordinary, especially because of field programmable gate arrays. They're so flexible that you can give a slow computer that could be very different and yet run a real software stack. RISC-V, most languages, and runs multiple operating systems and stuff. So it's a real system that you can go and play with.
Yeah, there's a follow-up question on that. Will RISC-V and processors based on it demand changes in the programming languages and in program design itself, or just in the compiler tools?
Yeah, no, that would be great, but that's not how the world works. Software is king, right? The software, all the applications are in whatever programming language is there, and the hardware has to follow the lead of the software itself. So if there now, a lot of the work that I've done in exciting is hardware software co-design, right? The software and the hardware work together, and in those interfaces. What's nice about machine learning stuff is these systems like TensorFlow and PyTorch are very high level abstractions, and they change quickly. So C++ is a pretty slow changing programming language, but these higher level platforms allow a lot of innovation in the hardware software co-design. So I think a version of that question would be, will there be opportunities in hardware software co-design to get better at security or other issues? And I think the answer is yes, but they're not going to go the other way around. They say, I put this hardware out there, it's got this feature, you better change your programming language to use it. That's not how the world works. The world, there's a bunch of companies that have tried that, and they've gone out of business.
Yeah, that's right. We would love to have Bjarne here to listen to this answer and really comment on that, because he was with us today.
Oh, that's great.
So, yeah. So we had a session with him today, and yesterday we had Guido, the creator of Python. So
no, great.
Yeah, great
good
sessions.
Good job recruiting.
Of course, yeah.
It must be the big speaker fee that you promised. That must be the.
I don't know. I'm just the MC. I'll take your concern to the team. Yeah, but thank you, David. I don't see any more questions coming, and we are also ahead of our time by 1 minute. Yeah, what I can say is thank you for your time. This was great. We really end this conference in a higher note with your kind of current and futuristic view of the computing architectures. So thank you for your time. I know it's been crazy times that we are living in.
Yeah.
So it's really a pleasure having you dedicate some of that time to us. Thank you so much.
Well,
David.
it's I think we're going to come out of this quarantine and learn some things. I think it's been really great that I could give a talk in Angola and didn't have to wait in customs at all. So
of course, yeah, that's the beauty of it. Yeah.
Okay, nice meeting you all. Good luck.
Thank you, David. Bye-bye.
Bye-bye.